Hi. So we are finally at the end of almost at the end of the sorting series, and we are going to talk about the balanced search trees. So let's look at them. So we looked at various sorting algorithms, and finally we looked at binary search tree, where worst case it can be n, but it's potentially log n. Delete. We looked at delete, and the challenge is ideally this is what we want, right? We want log n throughout. Both average case and the worst case. How can we do that? And we look at trees. We look at a mechanism whereby we can actually get that accomplished. So first, let's look at 2-3 search trees. What that means is that instead of just one value, one key per, one value per node, keys per node, it can allow it to have, more than one value. Okay. What that means is in this case, this parent has 2 nodes, but this parent has 3 nodes, and the value is also 2. It has 2 values, and what this will guarantee is that every path from root to the null link has the same length, and we'll look at as to how this can happen. And null link is basically the leaf, okay, and we'll see how that happens. And in-order traversal yields keys in ascending orders. What that means is sorting is you do an in-order traversal, and this is how you can do. And what is the property? Let's look at this 3-node element. In this case, all elements to the left are less than E. Elements in the middle are between E and J. In this case, it's H, and elements to the right are larger than J. So those are kind of the properties here. And okay, so let's look at them. If you want to search, that's obvious. Insertion is, let's look at what happens when you try to insert. And since the demo, is not obvious, I'm actually going to look at the web page to look at the demo. So let's look at them when you try to insert something, right? So search, we understand. Let's not worry about it. Okay, insertion. Let's say you want to insert k. In this case, you're trying to the moment you try to insert k in this tree, you will have to insert it at this end because it is greater than j. Now, but you have to make sure that the size is the same. You cannot just you can make this a 3-node element. So let's add k and l here, and that's pretty much it. And you have figured out how to insert. But now let's say you are now trying to insert something to S. You're trying to insert an S. And is there an example here? Okay, so there is no room for S here, right? So let's just assume that you can make it a 4-node. The moment you make it a 4-node, you can now split it and make it a 2-3 tree. What that means is you can just take E as the parent, and it will have 2 2-node elements as the children. And what about when you try to insert into a 3-node where the parent is a 2-node? What that means is that this is already a 3-node. Now you want to try to insert here, like Z goes here. Now obviously this is not acceptable. Then you'll have to move what? You'll have to move X up. And the moment you move X up, it will just go and sit nicely with the parent. But what happens when there is already the parent is already a 3-node element? So as you can imagine, it will go all the way up. If you try to move C here, then in A, C, D. If you try to add D, then C has to go up. Then this will become C, G. Now E has to go up, and so on and so forth. It's kind of recursive that way. But the moment E goes up, this is important. The moment E goes up, you actually split C and J into two nodes trees. Okay, so this is important. You will actually split them. You will no longer have them the same thing. You will actually just split them. And this is important, and the same way you can split from the root as well. This is an example where you have to add C. Your C goes up, and now you kind of split it multiple ways, and then you must split it, and you again split the 3-node to go at the top. So those are some things you'll want to do. So the way I look at all these things is, in an effort, why is it trying to do that, is to flatten the tree and to keep it well balanced. That's why you do all these splitting and things like that. That's how I read about it. And okay, so that's the basic idea. Okay, so let's look at, okay, so we looked at construction, that's obvious. Now the important thing here is that, let's say there are literally millions of elements between all the in all these subtrees, but when you split, you are actually just touching a very small set of these very large number of elements, very small. What that means is that the local transformation is always a constant number of operations. In this case, you're going to now move C to the top, and A and E will become two children. So that's the basic idea. The global properties, it maintains symmetric order and perfect balance. No matter what you try to do, these all properties are maintained, and these are some examples that show you how that is possible. And these are some numbers. Worst case is log n, and best case is between 2 and 3 nodes, right? So that's kind of what it means, and it is guaranteed logarithmic performance for search and insert. And that's pretty much it, so that's 2, 3 tree is something that you want to do going forward. And now there are various implementation of this concept of 2, 3 tree, and we'll look at one of them, how we can do that. Is red-black trees. Now just an anecdote, I always was confused about why it's called red-black tree, and Professor is actually somebody who invented that, and the reason for that is, I think he invented that, and the reason for that is that so this was invented at Xerox PARC, and that point of time they had invented the laser printer, and the red color was very distinct, and somebody liked the red color along with black, so they named it the red-black tree. So that's pretty much what all it is to that. I think it's a very interesting, nice story. Okay, so how do you do this? So let's say you want to represent the 2, 3 tree as a binary search tree. Okay, so let's say you want to do that. What you can do is you can use internal left leaning links as a glue for 3 nodes. What that means is you have 3 nodes. That's not really a binary search tree, but you like binary search tree. It has good properties and things like that. So what you can do is you can split A and B into 2, and this link between A and B is a red link. Okay, so B goes as the root, greater than B comes here, and A goes there, and that's how, and this is kind of the root. Okay, so this is the B goes as the root, and this is a red link. And the idea here is that when you try to split any such given 2, 3 tree into a red-black tree, then the one important property, as you can imagine, is that the black height of the tree is the same, right? Because you can collapse all these into one, and then you can imagine that these black links height will be the same. So that's what you kind of guarantee for a red-black tree, and you're simplifying this easy implementation when you're trying to do this. Okay, so what is a red-black tree? Once again, a binary search tree so that no node has 2 red links connected to it. That doesn't make sense. And this is most important. Every path from root to the null link has the same number of blank links, and that's what you define as, what you say as perfect black balance. And red links lean to the left. What it means is that given any node, the red links that it will have is always to the left. It will never be to the right. That's the idea here. Okay, so we looked at key corresponding red-black trees, and you can consider them as horizontal trees where this is to the left, and this is a 2, 3 tree, and search implementation is the same as binary search trees, exactly the same. It runs faster because of better balance. Okay, so as you know, the chances here that it will have very skewed is 0. It will not be the case. And okay, so this is just some implementation details. I'm going to skip over that. There are some operations that you need to worry about. That let's say that you have a right-leaning red-black tree. In this case, you'll have to rotate E such that such that E becomes something like this. Okay, after rotation, this is left. So what happened here? You had E S, and between E and S, and greater than S. That's all. And you moved, and so in this case, as you know, for binary search tree as well, this satisfies the binary search tree property, but this does not satisfy the red-black tree property. So you moved, S went to the root, E came down, and you made this leaning left. So that's what you do, right? So once again, if we look at these nodes, these remain the same, less than E and in between E and S, they remain the same. Well, this guy moved to E as well, and this guy stayed with S. So that's what happens. So those are the links you will have to change. And let's say if you actually want to do that, let's say you would at some particular point want to do this reverse. What that means is this is a perfect red-black tree, but you want to do it right-leaning, then you will do something very similar. And I'm not going. These are kind of parallel, symmetric operations. So I'm not going to go about this into detail. And then another elementary operation is recolor a split. What that means is, now in this case this is wrong because you cannot have two links from the same node to be red links. That's not okay. In that case, what you will do is you'll have to flip the colors for a node edge, and the way you'll do it is you'll move this to the top, and this is what you'll do, right? You'll move the red to the top, and then this will just be fine. And one thing so that's pretty much it. Now insertion. What's the strategy? Maintain a one-to-one correspondence with 2x3 trees by applying elementary red-black binary search tree operations. So that's why we learned them. These are helpful in insertion. So let's look at them. If you want to add a new node here, so this corresponds to this tree. So if you want to add a new node here, you rotate link red. So you can't really add this here. You can, because this will be, you want to add AC, but you cannot do this because this will be right leaning. In this case, you will have to rotate the link left, and that is what it will come as to. Now once again, insert, and so these are just some operations about insert, and I'm just not going to go over this in detail, but I think it's important to understand that the elementary operations are what are used. Maybe I can spend a couple of seconds here. In this case, if it is exactly one node, what do? You add if it is at the left, you add it here. That is okay. If it is to the right, that's not okay. You have to swap. Now if it is at the bottom, let's say you have to add here. We already saw what we need to do. And if you want to insert to a tree with exactly two nodes, let's say you want to insert it here. This is fine. Well, not really, because if this is large, search ends at this. Let's say you're trying to insert C, and then you try to insert C here, but this is not okay. So you kind of flip them both to black. Okay, so just to make sure why these things are, somebody might ask, you should ask yourself that why this is red, right? Why is this attached as red? Well, it's attached as a red link. It's made as a red link because the 2-3 tree, or the red black tree has an important property that the length of the black links from the root should be the same. And in this case, since this is red, then this has to be red, because this cannot be black, because if it is black, then this will be 1 and this will be 0, which is not right. So you start with the red, but in this case, as you can see, you cannot have two reds, so you kind of make both of them black. So that's the idea. In this case, once again, let's say you have C and then B, and you try to add A, then you'll have to add it as a red, and that is okay. But then the moment you do this, now what you will see is that you cannot have a node, in this case B, with both reds, right? It can have only one red, so you'll have to rotate. The moment you rotate, now you cannot once again. This is once again, this is true, right? You cannot have two reds here. You came back to look at the same situation, so you have to make both of them to black, and so on and so forth. So look at the between and kind of just reason about it. I'm just going to hold it for a second, and I'm not going to talk about it, but I want you to reason that this makes sense. Okay, so C and A, you're trying to add B. Think about it, why it should be red. Then okay, that doesn't make sense. It's right leaning. Go to the left. Then okay, this doesn't make sense because now you have two reds. You have to do something about it, and then you rotate light. Correct? Okay. So just to make sure, what is the operation that you're using here to do this? Let's go back and make sure we understand that operation. This is what we did, right? If we had two, if we were like this with, we were like this, we were Okay, so we use this, we use these elementary operations to kind of fix this problem here. Okay, fix this problem here if it is rotated, with two lefts. Okay, so just remember, if it has two left, two reds, then you can just move one at the bottom. And the insertion, now insertion to a 3 node at the bottom. So let's say, you have this edge, you're trying to insert edge, you have to insert edge here. Now that will not make sense because once again the 2 red is here. So you'll have to flip something, R and S, you move R up. And now once again there are 2 reds, which is not okay again. So you have to make them 2 black, but the moment you make these 2 black, hey, this looks kind of okay, but then this is red, so it is leaning to the right, so you have to lean it to the left. Okay, and insertion passing, okay, case 3. Once again, these are multiple cases. I would just like you to go over each of them and then figure out what's the right thing to do. And once again, this is some insertion, how do you build something up. We can look at them. Implementation code. Okay, but this is important, right? So now look at a red-black tree. In this case, you see how balanced this tree is. And in this case, look at the average, look at the optimal, and look at the max in 10. If you remember, in the binary search case, this was 16 for the same 255 nodes, random inserts. And this is you can prove that it is less than 2 log n in the worst case. And once again, why that will be the case, has the same number of black links and no 2 red links in a row. And that's pretty much what happens, and that's what you want to do. The delete is once again is log n. It's important. Once again, the delete is going to be tricky, and you have to be very, very careful when you try to do a delete. Okay, I told you about why it is red black is the razor printing, and that's what when Professor implemented it, he said that okay, I like the color red as a razor printer, and so it's important. Okay, deletion is important. You do not want to do this. This is bad. So think about deletion. There is actually a paper that you can look at the site and talks about delete really well. Okay, so that's pretty much it. The last slides are just some applications and various types of B trees that are just forms of red-black trees. I would let you think about it and read that up. Okay, thanks. Bye.